Hi, so today we're going to talk about mutually exclusive events and conditional probability a little bit. So today's objectives to determine whether events are mutually exclusive, to calculate probabilities when events are mutually exclusive, and to calculate and interpret conditional probabilities. So let's start with some basic probability notation. So probability notation is basically where you write uppercase P, parentheses, and then whatever it is you're trying to find. We kind of went over that when we did our lesson in class about kind of just the introduction to probability. But today I want to look at a couple more pieces of that notation. So let's say we have two events that we'll call A and B. If we wanted to represent the probability of A and B occurring, both of them occurring, the notation we would use is P parentheses A, and then this is the symbol we use for and. This is called an intersection because we want the intersection of both A and B happening at the same time. So A and B. The second one is if we're trying to find the probability of A or B. And in probability notation, when we're talking about the word or, that means one or the other or both. So technically, this is the probability of A or B or A and B. And the symbol we use for that is this kind of U shape. It stands for union because we're talking about the union of those two events happening, either one of them happening. So we kind of add. So we think of it as a union. And then the last one is what we call a conditional probability, probability of A happening given that B has already happened. And the symbol we use for that is just this vertical line. So probability of A happening given that B has happened. So A given B is how we would say that. Okay. Also, just important to know if you ever see a little C, like superscript, that means not. So probability of A with a little c superscript means A. Probability of A, not A. Cannot talk. Probability of not A. Now I want to look at some basic probability terminology. So some words that we use to represent different things. So firstly, let's talk about mutually exclusive events because that was in the title of today's lesson. So mutually exclusive means that the two events do not have any outcomes in common. Or basically, we're saying that the two events cannot both happen. It's impossible for them to happen simultaneously. There's no overlap. Nothing is happening in between them. So an example would be if I were to roll a pig dice or a coin or just a regular dice one time, that one dice roll cannot land on its back and its feet, or it can't land on heads and tails at the same time. It can't land on a 2 and a 3 on a regular dice at the same time. For that one roll, it's mutually exclusive, meaning that it cannot land on more than one side at a time. And then another word we have, and this is probably one you've heard of more often, is the word independent. And independent just means that the outcome of one event does not affect the outcome of the other event or the next event. So for example, if I'm rolling 2 pig dice, right, what happens on one pig dice is not going to affect what happens on the other pig dice. Those are independent, completely separate probabilities. Same with coin flips. If I flip one coin and then another coin separately, those two events do not impact each other in any way. They are independent. And one thing to keep in mind is that if two events are mutually exclusive, they are not independent. Mutually exclusive, by definition, means that if one thing happens, the other thing cannot happen. And independent means that they're not affecting each other. So if they're mutually exclusive, they are affecting each other just in a very specific way. So if they're mutually exclusive, they're not independent. So let's look at an example. This table shows data that were collected from people who attended a certain high school basketball game. It indicates the team each person rooted for, home or away, and whether the people purchased food during the game from concessions. So we have our table. We're going to use this table to answer a few probability questions. So let's start with, what is the probability that a randomly chosen person purchased food? We've done problems like this before, right? Basic probability, I'm going to divide part over whole. So people who purchased food was 160 out of 250. So again, my probability notation, I'm going to let F mean that they purchased food. I'm going to let H mean that they're rooting for the home team. So probability of purchasing food is 160 people purchased food out of 250 people total. I'm going to divide that. I'm going to get 0.64. So if I divide that in my calculator, I get 0.64. So that is my probability, 0.64 or 64% chance, but it's okay to leave them as decimals. Part B, what is the probability that a randomly chosen person supports the home team? So again, I had F mean they purchase food, H mean they root for the home team. So this one's notation would be P parentheses H, probability of home team. And total, I had 180 people rooting for the home team out of 250 people total. I divide that in my calculator and I get 0.72. So that's my probability. All right, so just basic using a two-way table to calculate probabilities. So now let's look at what we call an intersection. So what's the probability that a randomly chosen person purchases food and supports the home team? So when we see the word and in a probability question, we're talking about the intersection, that this person, we want a person who did both things. Intersection, not one or the other, but both things. So what I'm going to do is do my probability notation. So probability of purchasing food and, so that's my intersection symbol, rooting for the home team. What I'm going to look at on my table is I'm going to look at the intersection. All right, so purchase food and home team would be these 120 people right here. So 120 people purchased food and rooted for the home team out of 250 people total, which if I divide on my calculator gives me 0.48. Now notice for that and, unlike what we did with our pig dice situation, we did not do any multiplication. I just looked at the table and found where the intersection of those two events were. So my question now, related to our vocabulary for today, is are the events purchase food and supports the home team mutually exclusive? So I'm going to give you a minute to think. Are they mutually exclusive? So remember, mutually exclusive means that the two events cannot both happen. There's no overlap. They have no outcomes in common. So the answer here would be no. They're not mutually exclusive. And a good way to explain why is to give evidence from what you have. Basically, if they're mutually exclusive, then the probability of the and, or the intersection, purchase food and home team, would be equal to 0 if they were mutually exclusive, because that would not be able to happen. But since this is not equal to 0, we just calculated that it was equal to 0.48, that intersection probability. Since it's not equal to 0, those events are not mutually exclusive. So probability of food and home team was 120 out of 250, which was not equal to 0. So we know they're not mutually exclusive. In other words, there were people who did both. If they are mutually exclusive, then there would be a probability equal to 0 for that intersection. Part E, what is the probability that a randomly chosen person purchases food or supports the home team? Right. So again, when we talk about an or probability, we call this a union. In statistics or in probability notation, we think of that as one or the other or both. So what we're really asking is what's the probability that a person purchased food only, or supported the home team only, or were both things. So when I do this, when I think about how I did or in the lesson that we did in class where we did the pig dice stuff, my basic rule for or is that I add. Okay, so start with my notation, probability of purchasing food, or, that's our union symbol, supports the home team. So my basic rule for or is that I add. So let's try that. So I have 160 out of 250 purchased food, plus 180 out of 250 supported the home team. If I stop there, 160 plus 180, if I add those together, is more than 250. What's happening is that there are some people in that intersection who are being counted twice. So these 120 people who were both home team supporters and purchased food are being counted twice. They're part of the 160 and they're part of the 180. So by counting them twice, I'm overestimating the probability. So technically, at the end here, what I need to do is I need to subtract those 120 out of 250. We still are including them in the probability, but I don't want to include them twice. So my overall probability of or is I'm going to add probability of purchased food plus probability of home team minus the probability of both, and I'm just subtracting them so that they don't count twice. So that'll end up with 220 out of 250 which is 0.88 as my probability. So technically, we do have a formula for OR that is a little different from what we talked about in class because we're dealing with an intersection of things that are not mutually exclusive. So we'll look at that formula in a second. So what proportion of home team supporters purchase food? So now we're getting into what we call a conditional probability because we're saying of home team supporters. So I'm no longer talking about all of the people, the entire 250. I'm now talking about people who are home team supporters, and of them, what proportion of them purchased food. So we call this a conditional probability. So when I do my notation, I'm going to write it like this. I'm going to say, what's the probability that they purchased food, which is F, given, that's the vertical line, that they support the home team. So probability of purchased food given that they support the home team. And to figure that out, right, again, we do have a formula for given that I'll show you in a little bit. But we can just look at our table. Given that they support the home team means that I'm only going to care about this column of home team supporters. That's the only part of the table that I'm concerned with on this particular question. So in that column of home team supporters, I have 120 who purchased food out of 180 total. So 120 out of 180, which if I divide that is 0.667. Okay. Similarly, I could ask, what's the probability that a person who purchased food supports the home team? So I'm not just talking about all people, that a person in general who attended this game. I'm now talking about only out of the people who purchased food. So that is now a given. It's a conditional probability. So again, the way I write it in notation is what's the probability that they support the home team, H, given that they purchased food. So of the people who purchased food is my given. So again, I'm only looking at the row of purchased food, that top row. And in that row, 120 supported the home team out of 160 total. So 120 out of 160, if I divide that, is 0.75. So that is my answer. So using a two-way table, I'm really just kind of getting into the habit of, I'm using the table. I'm not worrying about formulas necessarily. I'm not overthinking about what's the proper way to do things. I'm really just thinking about realistically, logically using the table. But let's look at those formulas. These are formulas that are on your formula chart for AP Statistics, which is linked under resources on Schoology. I'm going to give you, there's two formulas that we're given for probability related to what we're learning right now. The first formula you're given is that conditional formula probability. Now, we just calculated two conditional probabilities without really using a formula. We were just thinking logically, looking at the table and what we had. And that is always an option. For most problems that you have, it's okay to look at things logically and think about what we would need to do. But occasionally, we're going to need a formula, and we'll look at some problems both today and next class where we might use the formula a little bit more. So my formula for probability of A given B is, we're going to do the probability of A and B, the intersection of both, divided by the probability of B, which is what we're given. So probability of the intersection divided by the probability of what we're given. And we did technically use that formula for the two given probabilities that we just found. We just didn't really think of it as a formula. The second formula that I get is the probability of A or B, that union probability. So the probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. And we did that as well in the example we just did, where we had to subtract that intersection because we didn't want them to count twice. So this is our official formula for OR, probability of A plus probability of B minus the probability of A and B. Now you might be asking, why didn't we do this on that day in class when we did our OR probabilities for the pig dice? So when we said, for example, what's the probability of rolling a pig dice and getting back or side? So I did probability of back plus probability of side. And I didn't have this in piece right here. Well, in that example, rolling one die, it is impossible to get both back and side on the same roll. It had to be one or the other. Those two events are mutually exclusive. And when they're mutually exclusive, that means the intersection probability of both things, is 0 because they cannot both happen. So technically, we were using this formula, just that in piece, the minus the intersection part was 0. So we weren't subtracting anything from the two added together. So this is our official formula for OR. We're always using it, but sometimes when they're mutually exclusive, that end piece is 0. So let's look at another type of problem where we don't necessarily have a diagram that's given. You have one answer already because I didn't do the pacing right. So a check of 100 randomly chosen classrooms at a large high school revealed that 48 of the rooms had refrigerators, 53 had microwaves, and 21 had both a refrigerator and a microwave. Right? So one thing I want to point out, when we say 48 had refrigerators, that means that could be rooms that have refrigerators only, but that could also be rooms that have refrigerators and microwaves. So when we're given a probability for an event, that could include that thing only, but it could also include some possible intersection. So it's the total people or rooms who had refrigerators at all. And 53 had microwaves at all. It could be just microwaves, that could be both. So part A says, are the events has a refrigerator and has a microwave mutually exclusive? So again, mutually exclusive means that they cannot both happen. There's no overlap. Well, we know from the problem that 21 had both a refrigerator and a microwave. That is our intersection. That's our and probability would be 21 out of 100, which is 0.21. That's not 0, so it's not mutually exclusive. For mutually exclusive, the probability of the intersection, I forgot to put a little symbol here, that intersection probability would be 0. And it's not here, so they're not mutually exclusive. So part B says, what is the probability that a randomly selected classroom has a microwave or a refrigerator? So again, you could find the probability. Okay. So let's let R equal me, meaning having a refrigerator, and M meaning having a microwave. So my notation for microwave or refrigerator would be R, U is for union, M. So refrigerator or microwave. Right? If you think about our formula or probability of refrigerator was 48 out of 100, plus probability of microwave is 53 out of 100, but I can't just stop there because if I add those two things together, I get 101, which is clearly more than 100, so that's not possible. We're counting the rooms who had both things twice, and we can't do that, so we need to subtract the intersection so that they're not counting twice. So minus 21 out of 100 gives me 80 out of 100, which is 0.8. So 80% or 0.8 of the classrooms have either a microwave or refrigerator or both. So let's look at some conditional probabilities. So what is the probability that a classroom with a microwave also has a refrigerator? So with a microwave means that it's given, we know this classroom has a microwave. Right? We've seen it in there before. We just also want to know what's the chances that they have a refrigerator. So the way I would write this, probability that they have a refrigerator given that they have a microwave. So I do want to mention here that sometimes that notation is going to feel backwards based on how the wording of the question is. But remember, what's given, what we know for sure is true, comes after the line. So it may feel backwards than how the wording of the question actually gives you the information, but what's given always comes after the line. Okay. So my formula for given tells me that I need to do the probability of the intersection, so both microwave and refrigerator, divided by the probability of what we're given, which is that they have a microwave. So out of the rooms that have microwaves, what proportion of them also have a refrigerator? Right. So probability of my intersection was 21 out of 100, which is 0.21. Probability of microwave is 53 out of 100, which is 0.53. So 21% have both out of 53% who have just or who have microwaves, would give me 0.3962. Part D is the same idea except backwards. What probability that a classroom with a refrigerator also has a microwave? So given that they have a refrigerator, what's the probability that they have a microwave? So microwave given refrigerator. So again, my formula tells me I'm going to do the intersection, microwave and refrigerator, divided by probability of what's given, which is that they have a refrigerator. So my intersection was 0.21. Probability of refrigerator was 48 out of 100, so 0.48, which gives me 0.4375. Then we have some more questions, which asks, what's the probability that a classroom has neither? What's the probability that a classroom has a microwave and not a refrigerator? So definitely can figure these out. If we think about the neither means they don't have one or the other or both. So one way to think of this probability is to do 1 minus the or probability, because or means one or the other or both. The only other option outside of that is that they have neither. So 1 minus my or would give me my neither. When we do the second one, if we kind of look at it critically, microwave and not a refrigerator basically just means what's the probability that they only have a microwave. So I could take that microwave probability and subtract the intersection, and that would leave me with the people who only have a microwave. So I can definitely figure these out, but there might come to a point with any of these questions where I might want a visual. So this is information that's given to me if I'm really good with formulas and I'm really good at like spatially, visually thinking inside my brain. I can definitely figure these out with just kind of thinking about the numbers and the formulas. But it might help to have some kind of visual. So I'm going to give you 2 examples of visuals that you can use for a problem like this. The first one is a Venn diagram. All right, so a Venn diagram where I have one circle representing those that have a refrigerator and the other circle representing those that have a microwave. And I start filling that in, right? 21 have both, so I'm going to put that in the overlap, the intersection. And then over here on the left side of the refrigerator, I'm going to put the ones that have just a refrigerator. That way the circle makes sense and it adds up to what it's supposed to add up to. So 48 total had refrigerators, but remember 21 are the ones that had both. So if I subtract 48 minus 21, I'm left with 27 who have just a refrigerator, right? 53 total have microwaves, 21 is in the intersection, so if I subtract, I know that 32 have just a microwave. Right. And then if I add those all together, that'll tell me who has one or the other or both. And then I know that the rest of the 100, anybody who's not included in one of these spots, is on the outside, so that if I add those together, I get 80. So I know 20 are on the outside who have neither. Right. So this is a good way to visualize what's happening. It kind of gives you an idea of where the numbers are and where they represent. Another thing that I could do is I could create a quick 2-way table where I have, do they have a microwave or not? Do they have a fridge or not? Right? So I know there's 100 total. I know that 48 total have a refrigerator, so I'm going to put that down here. 53 total have a microwave, so I'm going to put that over here. And then I know that 21 are in that intersection that have both. Now I'm going to do some creative subtracting here. 21 plus 32 equals 53. 21 plus 27 equals 48. So I can fill in those parts of the table. I can now do some subtracting to figure out the total number of people who don't have a microwave would be 47. The total people who don't have a refrigerator would be 52, because we know the totals need to add up to 100 in both directions. And now that I know those things, I can work backwards and figure out this intersection with people who have no fridge and no microwave would be 20. Right? So I can fill that out, and now I can use this table to calculate any probabilities that I'm given. So those are 2 options that you can use if you are a more visual person, if you want to have something to look at to figure out these probabilities. You don't want to completely rely on formulas and whatever. These are options that you can do. It's always a good idea to write things out or show visuals for your problem. So that is the end of today's lesson. I will see you guys next class.